So good afternoon, everyone. Welcome to this webinar. I'm very pleased to introduce my colleagues Arno and Evgeny, who are going to speak about measuring hardware performance counters on ARCHER2 using LIKWID. Gentlemen, over to you.
Thanks, Claire. Hi, everyone. I'm Arno Prume, and with me is Evgeny Belikov, and we are both on the ARCHER2 computational science and engineering team, helping support users of ARCHER2. So for this webinar, we wanted to present LIKWID, usage of LIKWID on ARCHER2, because we thought this would be an interesting tool for people looking to understand application performance by looking at hardware performance counters. So to start with an overview, LIKWID is a suite of command line tools that are meant to provide lightweight, portable, open source performance-oriented programming tools. There's a lot of different functionality that's offered. We're going to focus in this webinar on a number of specific tools and commands that we thought was likely to be of most interest to users trying to characterize application performance, possibly do some other things on ARCHER2. So in particular, we're going to look at the tools that can be used to do 4 key things that might be of interest, namely to probe the hardware topology of a given architecture. Of course, there are a number of tools to do this, but LIKWID provides another one. Understanding how LIKWID probes hardware topology is important because it gives us the basis for understanding how LIKWID sees any particular architecture that's running on, and in particular how other LIKWID tools refer to the underlying architecture when you use them. So the second of the 4 things that we thought might be of interest is LIKWID pin, which is a command line tool for controlling process and thread placement, well, in particular application thread placement. We also discussed LIKWID MPI run, which can be used to pin application processes. Then thirdly, we will get to the primary topic of the webinar, which is about doing hardware performance monitoring through using LIKWID perf counter to measure hardware performance counters. And as we'll see, LIKWID perf counter may not be enough, especially on ARCHER2, where users might wish to measure the hardware performance counters for MPI parallel applications, for which LIKWID perf counter itself is not that well suited, and instead we will extend by looking at LIKWID MPI run. Then finally, we will mention very briefly LIKWID bench, which is a tool to be able to run a number of different microkernel benchmarks provided by LIKWID to help both validate performance counter measurement using LIKWID perf counter and to understand upper bounds for hardware performance, concrete upper bounds for hardware performance, realistic hardware performance on a given architecture. I've included here a diagram of the architecture of the most recent sort of major release of LIKWID, LIKWID 5, which shows you how some of the various aspects of the design of LIKWID fit together. Going down from the command line interface tools themselves, which many of these are Lua scripts, there's C code, there's core C API, and that interfaces with various layers in order to be able to measure hardware counters, interrogate topology, etc. So going in order, which reflects kind of the order in which you might start to use LIKWID, and also reflects the order in which it's useful to learn about LIKWID because it supports using one tool after the next, culminating in hardware performance counter measurement. We will start with looking at topology. Just as a quick reminder, ARCHER2 nodes have 2 AMD EPYC processors. Each has 64 cores, 2 sockets, 1 processor per socket, 128 cores in total. We can use the LIKWID topology command to interrogate the hardware architecture. This tells us one of the things it tells us is the hardware threads that are available for any given application to use. So you can see it's recognized the architecture, and it's shown us the hardware threads, the physical cores, the corresponding die and socket, essentially the same thing, and those hardware threads which are available. So I've just presented this compactly. This shows, as you will see, that Liquid topology thinks that there are 255 hardware threads available. All of them are marked as available with this asterisk in the available column. That's because the AMD EPYC processors support two-way SMT parallelism on a per core basis. So unless you do what you normally do when you run parallel applications on ARCHER2, which is use srun and set CPUs per task to 128 and say hint equals no multi-thread, the SMTs, which disables availability of the SMT, of the two-way SMT parallelism. Unless you do that, all of them are available. And so if you run Liquid topology on a bare node just without srun, it will see that all these 255 hardware threads are available, but there are only 128 physical cores, of course. Next, the topological feature of interest might be just the zooming in a bit further on a single socket, so a single processor, where we know that the cores are divided up into CCDs, and those in turn are divided up into CCXs, as follows. Should say there's one level above that is the NUMA regions. So we have 4 NUMA regions per processor, each containing 2 CCDs, with each CCD containing 8 cores. So each NUMA region has 16 cores. So that is reflected in the topological information given to us by running Liquid topology in terms of what it tells us about the NUMA domain breakdown. It tells us there are 8 NUMA domains in total, and I've shown the first and the second and the final 2 here. So it shows us explicitly how it considers the core numbering within these NUMA domains, which is a useful reference. Zooming in further to a single CCD. Single CCD is 8 cores, which is composed of 2 CCXs, 2 core complexes. And there we see the cache level breakdown of the memory hierarchy. That information is also available through Liquid topology with the cache option. So that tells us about the nature and the size and the inclusivity of these of the different cache levels and how they relate, and which cores share L1, L2, and L3 caches. So that is a good starting point because it provides the basis on which we can understand the numbering used by Liquid when it comes to using the Liquid pin command or tool to pin applications. So Liquid pin provides a number of different syntax options for pinning application threads to cores. Threads can be pinned based on being assigned to lists of cores specified as a sequence of individual core IDs, which might be numbered according to whatever the OS thinks they are. They can follow either individual IDs or range notationed ranges of cores based on them belonging to a domain. The domain can be a node, the entire node. So we can, for example, use Liquid pin with -CN column 03 to specify that 4 threads should be pinned to the first 4 cores in the entire node. Similarly, there are other domain types in the syntax options which reflect socket level, socket domain allocation, die level domain allocation, cache group level domain allocation, memory domain allocation, etc., which allow very flexible assignment of threads to cores belonging to subsets of a given domain For example, in the third option, the socket-based allocation, socket-based pinning, we're saying there that there are 8 threads in total. We're assigning the first 4 threads to the first 4 cores of socket 0, and we're assigning the second set of 4 threads to the first 4 cores in socket 1. So there's a variety of options here that can be used. I won't go into detail in explaining all of these, but once you get the basic idea, you can work through this, and there's extensive documentation available on the Liquid wiki. The one thing to reflect to mention is that option number 5, the cache group numbering, that's based on the last level cache group, which in the case of ARCHER2 is the L3 cache. So in that sense, you'll be assigning cores within each L3 cache, so within each CCX. Option number 7, the CPU set, is mainly used not directly, but used internally within Liquid tools. So this pinning syntax is not just relevant for Liquid pin; it's relevant across the Liquid suite of tools, because that syntax is used both internally, how the tools communicate with each other and communicate with the core Liquid implementation. And so it's useful to be aware of this, regardless really of which tool you're using. As I said, there's lots of information about this on the wiki. So another way to see what domains are available and which concrete core IDs these correspond to is by using the -p option for Liquid pin. If you run that, you will get a breakdown of the available domains, numberings, and so that's the syntax that you can use and incorporate in your pinning expressions. This is just really another perspective on the information that's already present in the Liquid topology output, but in a convenient format that allows you to create pinning expressions. Just a note, as I already mentioned before, when we looked at the availability of hardware threads in the output of Liquid topology, you will see that in this Liquid pin -p output, core IDs from 0 up to including 255 are included. So that's again all the SMT, two-way SMT inclusive hardware threads, and that's simply because that Liquid pin command was run on a bare node without srun, without restricting, without turning off multi-threading. So if you were to run that Liquid pin option with as noted here, you would not see hardware threads 128 through 255. Okay. So if we actually want to measure things, we've looked at topology information, probing for topology information. We've looked at pinning using even without measuring, just using Liquid pin to pin any old application, because it could be convenient as an alternative to using srun on ARCHER2 or something else. It's just a convenient tool. Third of all, now we're looking at actually doing hardware performance counter measurement. So the first question might be, before we look at how to do so with Liquid, the question arises, well, what can we actually measure? So what the Liquid developers have done is they've gone and looked at the event available counter types, counter names, event types available for different architectures, and provided this conveniently embedded within the Liquid suite. So for the AMD Zen 2 processors that are on ARCHER2, the CPUs, those have each core has 3 fixed purpose counters, fixed C0 through 1 and 2, which are always assigned to store the 3 event types: retire instructions, inst retired any, actual CPU clock, and max CPU clock. There are also, in addition to that, each core has 6 general purpose counters, which arbitrary event types that are supported by the AMD Zen 2 architecture can be assigned to. And Liquid provides some ready-made assignments that are useful, as we will see. In addition to the core local counters, there are socket-wide counters for AMD Zen 2. These include, or mainly come down to energy counters. There are 2 of them, RAPL core energy and RAPL package energy. RAPL package energy works on ARCHER2, RAPL core energy does not. I'm actually unaware whether that's to do with the particular setup on ARCHER2 or whether that's to do with the event name not being entirely properly supported by AMD Zen 2. There is also, I say that, not entirely properly supported because actually there's a question about an additional category of socket-wide counters, so-called data fabric counters. Those are supported in principle. However, AMD doesn't appear to provide clear event names for those, at least according to the LIKWID developers. So they provide some option to use these, but without any guarantees. One thing worth mentioning when it comes to thinking about core local counters versus socket-wide counters is that, as we will see, all hardware performance counter measurements are done on a core-by-core basis. So you always specify when you're using LIKWID to measure counters, which cores you want to measure counters for. Now, that's fine if you're talking about core local counters, but if you're talking about socket-wide counters, the question arises of what are those associated with. So surely you don't want to count that socket-wide counter and aggregate it for each core that's part of the socket, because otherwise you'd be n-wise overcounting that counter. So rest assured there's a guarantee here. That's so-called a socket lock mechanism, which enforces that all these so-called uncore events are assigned to only one thread per socket. So in other words, they don't get overcounted. So don't worry about that. So we've seen what event types, what basic event types AMD Zen 2 architecture can provide in either fixed purpose or assignable hardware counters. The question is then, what do we actually care about? Often the things we care about are not directly those counter values, but rather the metrics derived from them that are more directly relevant to quantifying performance. In particular, the typical metrics are the number of flops, the bandwidth, measured bandwidth of L2, the measured bandwidth of L3, the main memory bandwidth, cache miss rates, load to store ratios, these kinds of things. And what's nice about LIKWID is that it provides ready-made recipes, so-called event sets and derived metrics, which are gathered together in performance groups, one performance group for each type of event set for each architecture, that combine the basic elementary counters for that architecture to give you the relevant metric of interest as a convenient output. So that allows you to do, for example, cross-architectural comparisons, knowing that you're more or less, at least if you can trust what the LIKWID developers have implemented based on the underlying documentation provided by the architecture providers, can trust that you're comparing like for like, more or less. So to show a concrete example of what this means, is very transparent, because these recipes are just in the LIKWID repository. So LIKWID is lightweight. It's kind of very everything's open source. You can see everything. So this recipe for example, the double precision flops event set and the metrics derived from them. So the flops DP performance group is this, everything you see here. That's it. So the basic events are these fixed purpose and assigned counters, fixed C1, fixed C2. Then the assigned counters, retired instructions, CPU clocks and halted, retired SSE, AVX flops, all and merge. And the derived metrics are as follows. Are there combinations of these fixed purpose and assignable counters, and these variables time and inverse clock, which core LIKWID derives not directly from the counters, but by some other mechanism, which is too much to go into here. But you can see very concretely how the output that you get when you measure performance counters and derived metrics, how it's computed. So it's all very transparent, and that's very nice. I think it's a nice feature of LIKWID. Okay, so we've covered what is possible in principle to measure on, for example, the AMD Zen 2 architecture. We've seen a recipe for what derived metrics you can get out for one case for flops. Now, how do you actually go about doing this? The command in question is liquid perf counter, as we already mentioned. That's the basic command for doing performance counter measurement. Liquid perf counter can be used in three modes, more or less. The default primary mode is so-called wrapper mode. What happens there is that you run liquid perf counter and you tell it which your application. It wraps the launch and teardown of your application and starts and stops measurement of counters when your application starts and stops. So you're assured that you're only capturing your application, nothing else. You specify, typically, you tell it to measure events and metrics for all those cores on which your application executes. So you're measuring your application everywhere it executes. That's typically the case. This is, by default, is whole application measurement, so start to end. You can use a very important part of Liquid, which is the marker API, that you can instrument your code, your application code, using this API to measure only specific regions in your code, typically what you know to be computationally costly kernels of interest. And then that means that only when your code enters those regions of interest, they can be multiple regions, they can be nested, only during those regions do the event counters get counted and aggregated into statistics. So that's very useful. Other modes are stethoscope mode. That basically is launched independently of your application, and you instruct liquid perf counter to sort of listen to, as a stethoscope, whatever happens to be running on the cores that you specify for the duration, arbitrary duration that you specify. And then what it outputs after it's done, after that duration is over, is the aggregate statistics of the events and metrics over those cores that you specified and aggregated over the duration that you specified. So single output at the end. So rather than rather coinciding with your application start and end necessarily, it just listens in and reports for a specified duration. So this might be useful perhaps if your whole application generates too much data, or or you just want to have a brief look at a sample over some phase of your application that you know is happening at any given time. But this mode, you should be aware that it can be used for monitoring, but it's for getting some assessment. But it's difficult to relate what is actually being executed, what part of your application is actually being executed, to relate that to the performance counters. And in particular, the marker API is not compatible with this. So you can't just over some duration isolate the statistics for only a particular kernel. Same applies to the timeline mode, in that it's still measuring your whole application, not just a particular kernel with marker API. Timeline mode is nice in a way because it essentially is like a live monitoring of your application, in that it periodically outputs aggregate statistics, aggregated again over the cores that you specify to measure, and regardless of what's running on those cores, better be your application, probably, if you care about that, and aggregated over the some duration time window, and then you get outputs, you get snapshots every time window. That's nice. So because you can gain insight into your application phases, but as it doesn't say here, but like the stethoscope mode, it can still be difficult to relate what application code is actually being executed. I mean, it can be nice to get some impression. At least you get some timeline, which is nice, not just aggregate over the entire duration. So what's nice about using Liquid to do performance counter measurement is that you don't need to do any code change to recompilation, unless you want to use the marker API. So liquid perf counter can be used with serial and with threaded OpenMP or p-threaded applications, but not naturally with MPI applications. You can get creative and use a parallel application launcher like srun with liquid perf counter to generate output, but that output will never be aggregated across processes. It will only be for each process individually aggregated. That could be useful, of course, for measuring load and balance. So if this is of interest, you could look at the tutorial for MPI Liquid on the Liquid wiki. What we will focus on is Liquid MPI Run, which supports MPI parallel application measurement of performance counters using Liquid Perf Counter for MPI parallel applications, and includes hybrid MPI plus threaded applications. This restricts measurements to Liquid Perf Counter's wrapper mode only. Does allow Marker API, and essentially what it does is it generates srun commands that launch Liquid Perf Counter. So it takes over your otherwise manual job of trying to get creative with using srun and Liquid Perf Counter, and aggregates the output across processes and threads for your application. Some options to be aware of, and this is documented on the ARCHER2 website now. We have a documentation page under data in the user guide under data analysis and tools for Liquid. So specify the total number of processes. So these are Liquid MPI Run options. You specify the total number of processes, the total number of threads per process, your desired pinning of processes and threads if relevant. And again, this uses the Liquid pin syntax, as I already hinted. You specify what you want to measure by saying the performance group, for example, flop CP or another one. Then I will skip no CPU bind for a second. Say, okay, go on to -S or skip, which is a way to skip shepherd threads, which are threads that occasionally are generated by OpenMP runtimes and/or MPI libraries and/or combinations thereof, which are hard-coded within a Liquid, but we suggest to always use -S XOXO, don't skip anything, because we've checked that there's no shepherd threads in any combination of MPI library and OpenMP runtime. Debug is useful because it gives you more transparency into what Liquid MPI Run is actually doing. As we shall see in an example, a few examples, is that Liquid, we can use the debug option to understand how exactly Liquid MPI Run is using srun and using Liquid Perf Counter in combination, which is important if you're going to take care to make measurements. MPI opts option can be used to pass anything that you want to pass to the srun commands that Liquid MPI Run generates. There's a pinning option, n per domain, which can be useful but only for pure MPI, and we accomplish similar in the example job scripts using -pin. Almost finally, -m activates this Marker API mode. Now, the one I skipped, the option I skipped, is the -- no CPU bind option, which is an ARCHER2 custom job, a custom option. It's not a bona fide Liquid option. We added it because essentially we wanted to provide a way for users of ARCHER2 who are used to running jobs the way that we recommend in the user guide, which leaves process binding to srun. We wanted to be able to do that because it's a natural, intuitive way compared to usually running jobs in ARCHER2. However, unless we introduce this option, no CPU bind, you're likely to run into conflicts where Liquid MPI Run tries to control process binding to CPUs through the srun CPU bind, CPU mask option, binding option, which tends to conflict with the way that we usually control process binding with srun. Therefore, this no CPU bind option is something that we have put in place in the central Liquid install in Liquid MPI Run that disables Liquid MPI Run trying to control process binding and just leaves it up to srun as usual. Okay, so let's look at some example job scripts and what we can expect and what this teaches us. So we wanted to focus on so Liquid is very, very nice, very seems like it's very useful to use. We wanted to provide people with some concrete usage to examples to remove the barriers involved in actually trying to get this running, because if you try it, you could run into the kinds of thread affinity conflicts that I already hinted at. And what's more, we wanted to provide kind of a unified approach, ideally using Liquid MPI Run, that allows people to do performance counter measurement for parallel applications. So a simple example is for pure MPI use case, having two fully populated nodes. So two nodes, each with 128 processes. So we specify nodes equals 2, 128 tasks per node, CPUs per task is 1. Set OMP num threads to 1. Export SRAM CPUs per task to Slurm CPUs per task as usual. This should all be quite familiar. And this is part of letting SRAM handle process binding as usual. So then we tell the IRON how many tasks in total using this Slurm variable. And there's no real other pinning options required because it's just going to fill everything up, all the nodes according to the total number of tasks. We use the shepherd thread skipping option as specified, and the no CPU binding as I already recommended. So this is not really too different from the standard. It looked quite similar to how you would run a pure MPI job with srun, just using liquid MPI run now with a couple of additional options. So before we look at any output from this, let's just look at a slightly simpler case because it'll be too much output if we look at output from 128 times 2 processes. So again, it's still 2 nodes, but it now have a much smaller number of ranks, just 2 ranks per node, so 4 ranks in total. Let's place things to have 1 rank per socket. So we ask still for 2 nodes. Now we have 2 tasks per node, 64 CPUs per task. Now we're spacing things out in the way that we would underpopulate using srun as recommended in the user guide for underpopulating using pure MPI. We set OMP num threads to 1 because this is still MPI, pure MPI, no threading, and we disable threading in the libraries. We set srun CPUs per task to Slurm CPUs per task, which is now 64, again as usual with srun, to allow spacing of the processes. And then we do need to specify pinning for liquid MPI run, and we have 2 options, 2 alternative syntaxes, both of which accomplish the same thing. One is to specify that the 2 processes on each node should be bound to the first cores of each socket, so core 0 to core 64. We simply know from our knowledge of the liquid of the topology of the numbering that 0 and 64 correspond to the first 2 cores on each socket. However, if we didn't know that, we could use the second spinning syntax, which is to say, take the first core on each socket. What is that? If we run this with xt high, so the example, as you see, doesn't run a bona fide application, while it runs xt high. That's useful just to see what happens. This just confirms that the affinity is as we desire on each node. If we run a bona fide application with the same options scenario and using CP2K, simple example, this shows that we get the individual core or each process. The output for each process is shown here. We get the event counters and the statistics for the event counters, and we get the derived metrics and the aggregate statistics for the derived metrics. Now, I said it would be useful to look at debug output. That is because if you use the --debug flag, you will get some additional output from liquid MPI run, which tells you the following. It tells you that what ends up being run in the final line is exec srun. This shows you the srun command that is actually executed. What it's running is not your application directly or liquid perf counter directly, but this liquid script, this .liquid script file. This .liquid script file, if you inspect it, and we've modified the debug flag to leave it there, is that essentially it just says that if my rank on the given node is 0, then I execute this first liquid perf counter command. If my rank if my local rank on the node I'm on is 1 out of the 2 on each node, then execute the second liquid perf counter command. And this is nice because this is very transparent and you can see exactly how liquid perf counter is being used. The shepherd thread skipping is being passed on. You can see the pinning syntax that's being used here to bind each process to the first core within the CPU set, the Linux CPU set that is being presented by srun essentially to each of these 2 ranks. Okay, so that was pure MPI. Pure OpenMP is similar again to ARCHER2, to the standard using srun. one task, 128 CPUs per task, set OMP num threads at 128, set OMP places the cores as usual, specify one process, set liquid MPI run, and use the -T option to specify 128 threads. If we look at the debug output from that, well, that actually is just a single liquid perf counter command with a quite transparent pinning syntax. So actually, this tells us we don't need actually liquid MPI run for this case. We could have used liquid perf counter because it's a pure threading example. So as follows, we could have simply used liquid perf counter directly with the first pinning syntax option is already familiar to you. The second one is a little bit more complicated. It uses the so-called expression syntax, which I will not go into here. You can consult the Liquid pin wiki page on the Liquid wiki. Then using a slightly more varied example, so we can use liquid perf counter to most easily, rather than liquid MPI run, to do more varied placement. For example, we know that the 4 cores in the CCX share an L3 cache. What we can do is to take 4 threads in total, put each thread on the first core of the CCX so that none of the threads share an L3 cache. Don't know why you would want to do that, but just as an example, and that can be accomplished by liquid perf counter with explicit core ID pinning syntax, with domain cache, last cache level L3 specific domain syntax, or with the expression-based syntax that I already hinted at. This is just xt high confirming that our placement is as we desired, and the results look similar to what we already saw before, broadly speaking in the format. It's just now that rather than each process reporting its output in a column and then metrics derived from that, aggregate metrics derived from that, we have each hardware thread reporting the metrics and the counters and the metrics derived from that. That's for running CPU without an xt high, of course, to get something genuine. And this can be extended, of course, now that you have now that you've looked at pure MPI and threaded, we can combine the two to hybrid MPI plus OpenMP. And again, it looks similar to using srun as usual. So we set srun CPUs per task, etc., and then we specify the number of tasks in total using the slurm and tasks variable. We specify 64 CPUs per task, threads per liquid MPI run process. And alternatively, we can use the following pinning syntax. So these examples are in documentation, and the serial case follows quite straightforwardly. Won't cover that. Okay, so we've looked at concrete examples and recipes, which hopefully be useful to actually figure out how to run what you might want, different scenarios for running, depending on what your application, what kind of parallelism your application has. So I'll very briefly cover the fourth topic that I wanted to cover about a topic of interest for Liquid, which is microbenchmarking. So Liquid provides an ability to perform microkernel benchmarking through the Liquid Bench tool. What that is so Liquid includes a series of tests for each of the derived metrics in the performance groups that are composed of very basic assembly instructions, where a priori the number of operations of various kinds are known. And that means that knowing just those number of operations of each kind and knowing and measuring the CPU clock, you can compute what the flops should be, or what the cache misses should be, whatever, and then you can compare that to the results that you're getting with liquid perf counter based on the event counters and the metrics derived computed from them. And so here's a comparison between the reference, which is the a priori liquid bench pre-computed known correct values, and combined with actual CPU clock data, and what is measured using liquid perf counter. So this is very useful. It's useful for A, validating that liquid perf counter is operating as expected, B, providing estimates of concrete upper bounds on performance, hardware performance, which rather than just the vendor provided theoretical maxima, which can be used as an input to roofline analysis. And you can also create your own benchmark kernels based on this. Okay. With that, I hand over to Evgeny.
Okay, hi everyone. I'll switch over. So I'll continue on speaking about the Marker API, which is another feature of Liquid that allows us to measure in a more fine-grained way the regions of the code that we want to look at. So the Marker API is a bit more involved, the usage. It requires recompilation, but it can be done in a fairly surgical way by adding a few macro calls or function calls, if you prefer. And this way, if we know, for example, from profiling that we've done before, we know where regions of interest are for our application, and when we want to zoom in on those. We don't want to simply run Liquid on the whole application. This would include I/O, some maybe some loops we're not interested in. So we add the macros that I'll show on the next slide, and we need to recompile it with this -d liquid underscore perfmon flag set, along with at compile time, we need to point to the location of the libraries, which is done with reference to this with -I and reference to this liquid dir environment variable, which is set by the module. When you load liquid module, then liquid dir will be set, and under there is include where the include files are, which we need to include in the code. And then when we link, we need to also refer to the location where the libraries are with capital L, capital L, liquid dir lib, and refer to the library name, which is lib liquid, so it's -L liquid on the link line for link flags, and we adjust the LD library path accordingly. So this is because it uses the LD preload mechanism, where it substitutes an original call with a call to liquid, which is then forwarding and on to the original call while doing some setup. The application must be dynamically linked, but most applications are dynamically linked by default on ARCHER2. And then we can run using liquid perf counter or liquid MPI run with the -m flag to enable Marker API. There's a caveat that we should avoid calling this in the very innermost hot loop regions, because each micro call is still associated with some added overhead over time. So the Liquid uses hash tables to store performance counter data, which is fairly efficient, but if we really push it, then it will create overhead. So we need to be careful. And we can use multiple regions. So for multiple loops or multiple functions, for example. This is how the Liquid Marker API looks like. I didn't include any code here. This is only the code to be added to enable, and this is the Liquid Marker API example using C, but there is also support for Fortran and other languages like Python, Julia, Java, and probably some more. So we need to include the Liquid Marker header, and then in the sequential part of the code, we call the Liquid Marker init macro. Then we encapsulate the region with marker start and stop. Start and stop with a tag, which is a string, which should be unique. And then start and stop instructs directly Liquid to start measuring and stop measuring again. So this way we can really focus on a small region of the code. This Liquid Marker register is not strictly necessary, but it's recommended by the original developers. to reduce overhead. So there's some setup originally. If your code is using OpenMP, marker register, marker start, marker stop should be called from inside the parallel region. And finally, again, in the serial part of the code, liquid marker close kind of finishes off the measurements, and after that, the markers can't be used anymore. So this is simple output of a serial hello world application. It only calls the printf function, but to give you a flavor of what output you might get. So here we use the mem group of events. So we get some, as expected, not much data, but just to visually show you. So we would see some DRAM traffic for the mem output and memory bandwidth and data volume as summary at the bottom. This shown only a single thread as a serial application, but if it was a multi-threaded application, there would be different thread summaries for each. So this is a quick overview of the Marker API. Another use case I would like to briefly highlight from kind of high-level point of view is the roofline analysis. So some of you might come across it. If not, this is the original paper by Williams from 2009 about the roofline model, which I will briefly explain on the following slides. But this is the reference if you want to look it up. So roofline analysis can be done with Liquid on ARCHER2. There are other tools that support it, but Liquid is one other way to get to the numbers. So roofline model is a visual performance model that defines sort of empirical bounds on performance, and then the hot loops we can place as dots on a roofline plot. And it's based on this idea that performance is mainly limited, on the node, I should say, mainly limited by memory performance. It's how quickly we get instructions and data into memory and back, and by peak flops. Memory performance can be bound by running something like the stream benchmarks, which is commonly used to get the attainable performance with a triad code or load. And those are also included in Liquid Bench. And I'll give an example. And then let me move on to like the visual representation of this. But we've got on the y-axis performance, and on the x-axis is the application characteristic, which is operational intensity. It captures both memory and flops performance as operational intensity, flops per byte metric. So we can get a graph like this. This from Wikipedia is schematic. It's not a graph for ARCHER2 directly, but we could get a figure for every architecture. We can get a roofline defined by running stream to get the slanted roof, and to get the horizontal roof for peak performance, either from theoretical numbers, we can estimate from number of cores times the frequency, and then we can get different values, whether we're using, for example, single precision or double precision with vector instructions like SSE or AVX. But the idea is that through two measurements, we define this limit. So the slanted roofline and the horizontal roofline, and our applications, we can then again use Liquid to measure application characteristics like flops and bytes. And then we can place our loops or applications, in this case, we call them app 1, 2, 3, onto the roofline plot. And what it gives us is a quick way to see, is our application memory bound or compute bound? This is based on looking at the ridge where the two rooflines overlap in the roughly middle top of the screen. And then if we plot a vertical line through that ridge point and the x-axis, then we can see some applications might end up under the slanted roof on the left of this line, or others will be on the right of this line. And the left are the memory-bound applications, and on the right will be the compute-bound applications. So this is a way to assess boundedness, and which we can also see already roughly from the operational intensity for each application. But it's also a way to see how much optimization potential is there for a given loop or function or application that we're investigating. And this is represented by the distance from the roof lines. For example, app1 is memory bound in this case, and we see that it's fairly far away from the slanted roof, so it would be worth looking into optimizing it and moving it upwards closer to the limit. And if we plotted stream triad microbenchmarks, it would sit roughly on the line further on the left, because it's a streaming kernel, and there's little we can do. So it's used to define this line. So we can also define for cache-aware roofline. We're not going to go into detail into this, but there could be another line on top of the memory line. If we manage to push through the RAM limit, then the last level cache will place another limit, and so on. So it's kind of bounds and bottlenecks and others that we can do. So I think we're coming to the end of the slide. So this is roughly the overview. And we can use Liquid Bench for this, as it includes, for example, microbenchmarks for loads and stores. And it includes various benchmarks for computational benchmarks to get peak flops with or without AVX, for example, for double and single precision, and so on. So roofline can be useful to tell us whether the loop is memory or compute bound, and shows some optimization potential for those loops or applications. But it doesn't tell us what the optimizations are. We still need to think about how can we reduce, for example, the memory footprint, or restructure access to parts of our data structures to get more locality, temporal and spatial locality, where we can reuse some of the data that already got fetched into the cache. And we can also use Marker API to get those loops. So it doesn't have to be on application basis, because it's then not very fine-grained. But with the Marker API, we can really drill down into the hot sections of our code to see how much is left to optimize. So this view is very focused on node-level optimization, but often it's an important step to get efficient application overall. With this, let me conclude. I hope this was a useful introduction to Liquid. Few users were waiting for it for a long time to happen, so now Liquid is available. Please go ahead. We encourage you to give it a try and use it. It's a powerful set of tools where there are many tools, and each of the tools does this thing well. We're in the Linux philosophy. So there's 2 links at the bottom for the Arch documentation to summary of the sections, and you can copy paste some of the scripts to use and adapt. And there's the Liquid wiki, where much more in-depth information is available. We've got a few minutes for questions. Thank you very much.
So yeah, I'll definitely echo what Evgeny already said, and encourage anybody who was interested in trying this to give it a go. And if there's any particular scenario placement scenario, measurement scenario that you're trying to work out how to make work, and it's not working, or you're wondering, just feel free to contact the help desk to ask for support on that. It would be interesting to us as well. As I said, the debug option is very useful because it's important to know exactly what you're measuring and where. The fact that we disabled the CPU binding is useful. It does mean that you need to be taking care that all the recipes we've provided should work for the examples. You need to take care if you're adapting it. You might end up in a situation where if you're not careful, it's possible to potentially measure the cores on a subset of the ones on which your application is actually running. But if you follow the recipes, it should probably be all right. But as I said, use a debug option. Use XT-high as recommended in the documentation before your application, but launched in exactly the same way, so that you can see exactly what is happening, and so that what you think is happening is actually happening, and that what you think you're measuring is what you're actually measuring. So care needs to be taken with this tool. It's powerful, but you also need to take care to interpret it correctly. Okay. Doesn't seem like there are any questions. So in that case, yes, thank you everyone for attending, and get in touch if you want to ask anything to follow up on this with the ARCHER2 help desk.